morning, everyone. Thank you so much for joining today's webinar, UCIe Packaging Technologies, presented by Gerald Pasdast. He is Intel Senior Principal Engineer and UCIe Form Factor Compliance Working Group Chair, and Stefan Rusu, TSMC Senior Director and IEEE Fellow. At this time, I will pass the microphone over to Gerald with a couple of reminders. One, we will have a Q&A session at the end of the webinar. If you do have a question during the webinar, please submit that through the chat feature, and please mute your microphone if it is not already muted for you. Thank you so much, and Gerald, take it away.
Okay, thank you very much. Good morning, everybody. Just a quick disclaimer that the information in this presentation may refer to specifications still in the development process. This presentation may reflect the current thinking of various work groups, but all material is subject to change before the specifications are released. The agenda for today, let's just go through that quickly. So we'll take a couple of minutes out to walk through a fairly quick intro recap of the Q1 webinar we held with the UCIe overview. This was an overall overview of the architecture and everything, so just spend a couple of minutes on that. We'll discuss the laminate and advanced package flavors of UCIe, walk through OSAT packaging technology offerings, and then we'll wrap up with future directions and conclusions, and then have a live Q&A in approximately the last 10 minutes of the webinar. UCIe has 120 plus member companies and growing fast. We have leaders in semiconductors, packaging, IP solutions, foundries, and cloud services. Cloud service providers, they're all joining together to drive the open chiplet ecosystem. As you can see from the logos of the promoters and board member companies here, a lot of big names, a fairly good cross-section. Maybe you can argue most of the big names in tech are involved in here. So it's exciting stuff. UCIe Consortium welcomes interested companies and institutions to join the organization. There's a link there for your convenience to join or learn more, UCIeExpress.org. And membership is open for both contributor and adopter levels. UCIe was founded in March of last year and incorporated right at a year ago, last June of 2022. And as I mentioned, two levels of membership, contributor and adopter. I won't go through every single line item in here about what contributor and adopter membership includes, but I'll just pause for a moment. You can take a look at it. Both levels of membership allow for access to the final specifications. There's IP protections involved in both of them, and attending various work groups and industry events. But in addition to that, at the contributor membership level, there's also participation in the technical work groups that we have. Towards the end, we'll list out what technical work groups exist. The ability to influence the technology as well. So this is participation in the work groups, bringing up engineering change requests, bringing in new feature requests. And at the contributor level also, there's going to be yearly board member elections held. So as a contributor level, anybody can throw their name in the hat for that. Okay, so as I mentioned, in Q1, we did the first of the series of webinars. This was the overall overview of UCIe, and there's a webinar link there. It's a YouTube video. You can watch it. It's an hour long. I highly recommend you watch it if you are not very familiar with what UCIe. It's a very good intro for you to learn. And I'll give you an even shorter intro now. So what is the motivation of UCIe? It's the fundamental goal is to align the industry around an open platform for enabling chiplet-based solutions. So if we take a look at the cartoon picture on the left, at launch, UCIe provides 20x the I/O performance at 1/20th of the power versus off-package SerDes. And the gap becomes even more prominent as packaging technologies advance and the pitches get smaller and we have more advanced capabilities coming online. In this particular example, hypothetical example, you can see an SoC construction that is chiplet based. So for example, you have a sea of cores maybe sitting in the center. That's the blue chiplet sitting in the center there. You're surrounded by memory chiplets. You have other customized IPs, maybe stacked. You have some other thing on the sort of the, I guess, the upper right of this picture where you have a UCIe connection there. That could be an accelerator chiplet there. It could be an I/O chiplet. It could be anything really. And the other flexibility that this provides is within the same package, you can have 2D, 2.5D, and 3D type of solutions in there. So with the combination of all of these different things, you can really, it really opens up the, the door to innovation compared to the standard way of constructing SoCs, you know, up until relatively recently, which is just a monolithic piece of silicon there. So some of the advantages over here are you're no longer constrained from reticle limit silicon. You can have multiple smaller silicon, you can have different size silicon, and you can interconnect them. It reduces the time to solution or time to market, enables die reuse, and also lowers portfolio costs. So what does that mean? Well, usually compute elements, things like cores or accelerators, you want them to be on the latest and greatest process node generation to get that C dying reduction and best performance per watt. And yet you may want to reuse an older generation I/O or an older generation, some other type of functionality that isn't as important in terms of compute efficiency. It could be something that is a more mature process node for I/O, or something that requires a little bit more mature process. So when you also have a chiplet-based construction method, you have smaller die, you get better yield, reduces IP porting costs, overall product SKU cost gets reduced, and it also enables you to mix and match different die and come up with bespoke or custom type solutions faster. So if we take a, this is the last foil for the overview of UCIe that I have for you today. If we take a look at the picture on the right, UCIe, the way we approach it, it's a layered approach, layered architectural approach. You could see starting from the bottom, we have the physical layer, which is what most people think of when they think of die to die. But with a physical layer only, it only takes you so far. Sure, electricals and mechanicals can be taken care of there, but unless it is widely adopted, you usually have your own die to die, and you can't really interoperate with others. But on top of that, you really need to have some idea of what the protocol is going to be, because electricals alone are not going to guarantee industry-wide interoperability. So we have a physical layer there. Physical layer, you can see a box to the right of it. It has what all the features are implemented in there. What are the functionalities implemented in there? You have a die-to-die adapter. The adapter is a very important line item here. This one contains the support for multiple protocol mapping to the physical layer there, and there's some additional notes there for what it contains. And of course, the protocol layer flexibility above that, we've launched the specifications with CXL and PCIe for volume attach and plug and play. CXL PCIe can address a common usage cases such as .mem, .io, accelerator attach, multiple different versions you can do. We also have a streaming mode. This is very important. You are not constrained to only CXL PCIe. You can have really any protocol, your favorite protocol, mapped through a die-to-die adapter to the physical layer. So we do support that. Fairly important and popular protocols such as AXI, CHI, SFI, CPI, all of that can be mapped on there. And we also have raw mode support. So if you just have raw bits, you want to completely bypass the adapter, you could do that as well, go straight to the physical layer. So all of that is supported. And I, again, encourage you to watch that video from the Q1 webinar. It goes into much more detail. Next up, let's talk about laminate and advanced package support for UCIe. So UCIe supports both laminate packages, otherwise referred to as standard packages, or 2D configurations. These, generally speaking, are more cost-effective, and you have more flexibility on the package to place your die. In other words, you can go longer distances, you can have 90-degree connections, you can do a lot more type of things there. We also, and there's a cartoon to the right of it of a standard package cross-section. Fairly straightforward. You're just using front side strip line layers of the package to interconnect your die there. We also have advanced package support, otherwise referred to as 2.x or 2.5D. These are more power efficient. The channels are much, much shorter. You have less flexibility on how you place your die in the package, but the channels are shorter and you don't need as much signal integrity features. For example, there is no RX termination required at higher speeds. So the power efficiency goes up by about a factor of 2. And you have, if you, for the absolute highest bandwidth density, that's the choice to go for. Because of the smaller bump pitches, you get to pack a lot more wires in a smaller area. Important to note that dies can be manufactured anywhere and assembled anywhere. In other words, this is very IDM and OSAT portable type of technology. And as mentioned earlier, you can mix 2D and 2.5D in the same package to give flexibility for the SoC constructor. And pictures on the right for 2D as well. Just to very quickly, Stefan is going to go over this in much greater detail than myself. But in this example, you can see cross sections of silicon bridges, interposers, and fan-out RDL type technologies. These are all considered advanced package technology. In the tables over there, just to quickly go through there, we range from 4 to 32 GTS data rate for both the standard package support as well as advanced package support. So 4, 8, 12, 16, 24, 32 GTS. The width or configuration of each module or PHY for standard packages of I-16 full duplex. So you have 16 outbound main band lanes and 16 inbound. And for advanced package, it's a by-64 configuration. Bump pitch ranges there 100 to 130 microns for standard package, 25 to 55 for advanced packages. There's some notes there for channel reach, up to about 25 millimeters at the maximum 32 GTS speed. And an advanced package, just due to the physical construction, bump pitches, and the way that OSATs generally place the die next to each other, usually the channel turns out to be less than 2 millimeters. And we have some bandwidth, both shoreline bandwidth or linear bandwidth. This is gigabytes per millimeter metrics there for you for standard package as well as advanced package. That range there, by the way, it is a direct mapping to 4 GTS, which is the minimum number, and 32 GTS. So 28 gigabytes per second per millimeter refers to 4 giga transfer operation. 224 gigabytes per second here refers to 32 GTS operation. Same line of thinking for advanced package. You could see a fairly significant bump up in bandwidth density. And then we also have aerial density or bandwidth per millimeter squared, standard package range, and advanced package range. Okay, so let's move on to the standard package version of UCIe. We call that UCIe-S. S stands for standard package. And we have 2 options for you to consider. We have a by-16 or single module depth configuration and a by-32 arrangement, which is in other words, a stacked module arrangement. That's 2 PHYs stacked on top of each other. And for the single stack, you require a 4-2-4 type of package stack up in order for that support. You need 2 routing layers for that. 2 strip line topside routing layers. And for the stacked or the by 32 module, an 828 type of package stackup is required. So 4 routing layers. And really the key here is when you will use the by 16, if you happen to have a package that has less layers in it, and perhaps you don't have as much bandwidth density requirement. When you move to the by 32 module, it means you have the package available that is capable of supporting it. And also you want to double up on your bandwidth per millimeter escape. So you have twice the number of signals, it's 32 instead of 16, you can double your bandwidth. One more note that I will just throw out here is if you take a look at the data rate support that we have, which is from 4 to 32 GTS, that's an 8x difference. And then you have per millimeter of escape, either a single or a double stack or a by 16 or by 32 configuration that gives you another 2x bandwidth density increase. So taking data rate and this page over here, which is the single or double stack into account, which is another factor of 2, you have essentially a 16x range of bandwidth per millimeter flexibility at your disposal to play with. Data rate plus 16 or 32 module. So 16x bandwidth per millimeter is a fairly wide range to give the flexibility to the SoC constructor. Okay, so the cartoon in the upper left-hand corner here is to show you what the arrangement of that by 32, this is the example we used here, is the by 32 it looks like. So if we look at that, die number 1 essentially has 2 of those by 32 configurations put side by side. With the laser pointer here, I will circle. This is one of the by 32s. You can see that the transmitter and receiver portions are checkerboard, are placed as a checkerboard type pattern. And then here's the second by 32, what the laser pointer is circling. And you have the same thing on the die number 2, and the red arrows show the connections between the transmitter and receiver submodules. And this checkerboard pattern is fairly important for interop and mechanical compatibility of die and how they're arranged. When you rotate a die, when you mirror a die, this checkerboard pattern becomes very, very convenient for making sure all the wiring is capable of being done. Here's a 3D picture rendering of what the vias in the package look like, and you get sort of an idea of the power vias over here in red. You have ground vias in green, and you have signals transmit and receive in the blue and the yellow here. 18 I/O per millimeter per layer. As mentioned, 2 routing layers and 4 routing layers, depending on whether you have a by 16 or a by 32 configuration. Here's a cross section of that package, the vias in the breakout here. It gives you an idea of at least 2 of the layers of signaling layers that are being broken out, how they fit with respect to the grounds and powers. In the specification, the electrical specification, we address insertion loss and crosstalk with the voltage transfer function, VTF. In this example, we have an eye diagram for you at 32 gigatransfers, what that representative eye diagram looks like at 25 millimeter channel, the maximum 25 millimeter channel at 32 GTS. And you could see at Nyquist 16 gigahertz, which represents 32 GTS operation, we have about 8.7 dB of insertion loss. And this includes the RX termination as well, by the way. And then if you look at the cumulative crosstalk at 16 gigahertz Nyquist or 32 GTS data rate operation, we have 31 dB of crosstalk suppression. So UCIe advanced bump maps, to walk you through this quickly, we have in the specification today, you will see there is a 25 to 55 micron bump pitch support. And depending on where you are in terms of region of bump pitch, we have different maximum data rate supported. This should make sense intuitively. As you go smaller and smaller in bump pitch, you have less area to put circuits, and smaller circuits generally, when you have less area there, some of the features you need, for example, clocking and training features, you start having lesser and lesser area to put that in there, and even the drivers and receivers. So, and power delivery becomes a great challenge at smaller bump pitches. So we have a guideline for maximum data rate per bump pitch already in the specification. And also, as the bump pitch changes across this fairly wide range of 25 to 55, you'll want to have the flexibility of different bump maps, but supported bump maps to give you the ability to make sure that you're doing it correctly and you can interoperate between any flavor of bump map. So for example, in this region here, 38 to 50 micron bump pitch, we recommend a 10-column configuration for the bump map here. And as you go smaller in bump pitch, in order to really take into account that full X and Y critical dimension shrink or reduction in bump pitch, what you want to do is take both X and Y reduction. And what that really translates to is you want to reduce the number of rows and increase the number of columns. If you imagine for one moment, if you were to maintain the 10-column design when you go down to 25 micron bump pitch, what that would really translate to is you have not at all taken in any advantage of the X pitch reduction that's allowed to you. You've only taken into account Y pitch reduction. In other words, you're taking a linear reduction in area, not that square law reduction in area that you're afforded when you go to smaller bump pitch. Similarly, but differently, in the opposite end of the spectrum, when you, as an example, go to 55 micron bump pitch, what you want to do is have the flexibility to go to this 8-column design. And this is important because if you don't have this flexibility, if you stuck with the 10-column design, what would end up happening is, in order to meet the diagonal critical dimension or minimum diagonal design rule, you'd have to abnormally stretch your Y in order to meet that diagonal minimal rule. In other words, even though you can lay it out, you were going to unnecessarily increase the height of your bump map and therefore burn more silicon area just because you maintained an unnatural or unoptimized column count. So essentially, you're trading columns for rows as you traverse the bump pitch range there. And we have a guideline for bump pitch range per module arrangement. Okay, this foil here is just to show you in graphical form how this area efficiency works. So orange represents that 10-column design, and at 45 microns, you get, we've anchored it here. This is the figure of merit for 100% bandwidth efficiency I'm sorry, aerial efficiency. So this is 45 microns at 100%. And the green figure, or the green waveform here or plot here, is essentially showing you the 16-column. And once the orange and green, or 10 and 16-column plots cross each other, that's essentially the point at which you want to cross over to the 16-column design and get above 80% aerial efficiency. And similarly, in the opposite direction, when you cross roughly this point here, that's when you want to cross over to the 8-column for that aerial efficiency. One final comment about this thing: while something over 80% is pretty good for the smaller bump pitch range, the reason why that's important is, if I go back to the previous foil here, the height of this thing, the magnitude of the height here is relatively small. And therefore, having 10 or 15% inefficiency doesn't really hurt you from a number of microns, practical number of microns point of view. However, if I have 15% inefficiency for this much taller bump map, that's more than 2x taller than the lower end range bump map, you know, every single percentage counts more in terms of raw number of microns. So what we really want is, for the higher end of the bump pitch range, we want to have greater than 90% efficiency. And then at the lower end, something above 80% is fairly good. So UCIe-A, quickly, the arrangement for this, we have transmitters closest to die edge with receivers stacked on top. The red arrows show essentially the connection there. And similarly, voltage transfer function, in this case, we're showing you a 16 gigatransfer I diagram along with the I mask in the specification. And you can see the insertion loss at 8 gigahertz Nyquist is about 2.8 dB. At 32 GTS, you'd have about 7.5 dB insertion loss. Not too different from the standard package version. Crosstalk at 8 gigahertz Nyquist, you have about 25 dB suppression, and at 16 gigahertz or at 32 GTS, it's about 28.5 dB. This is the final foil I have for you before I hand it over to Stefan. One of the key components of UCIe-A is interoperability, backwards and forwards interoperability. That's very key for any standard to be adopted and widely used. You want to be able to reuse older chiplets with newer chiplets. You don't want to have to throw things away and redesign them every time there's a new spec release. So for UCIe-S, the standard, you have a little bit more flexibility on how you route your signals through the package to make them work. Although over there we have rules for interop as well. But for UCIe-A, just to demonstrate and make sure everybody understands this, there are two key factors in ensuring forwards and backwards mechanical interoperability of different generations of UCIe-A. So first and foremost, you have to keep a fixed shoreline. In this case, we have a 388.8 micron shoreline per phi instantiation, and you must follow a specific signal ordering rule in your bump map, which we have specified in the spec. So as an example in this cartoon here, if we look at on the left, you have a 55 micron bump pitch instantiation talking to a 55 micron implementation. And you can see they have 4 rows and 6 columns in this simple cartoon diagram. When I have the same 55 micron implementation talking to a 40 micron, as I mentioned earlier, we've changed the number of rows versus columns. So now we have 2 rows and 12 columns, but I maintain the signal ordering, or as I go from left to right, the bump ordering of signals is maintained here with respect to the other version, 55 micron, and I maintain the same shoreline of 388.8. And because of that, I'm still able to connect up everything very similarly as I did when I had the same bump pitch on both sides. So that's a very important rule to follow, and that ensures that we have interop across multi-generation implementations of UCIe. Finally, UCIe 1.0 delivers the best KPIs while industry-leading KPIs while meeting the projected needs for the next 5 to 6 years across the entire compute continuum that we've looked at. And with that, I would like to hand control over to Stefan Rusu, my colleague, to talk to you about different OSATs and technology offerings. Stefan, the floor is yours.
Yeah, thank you, Gerald. And good morning, everyone. I will focus on the leading UCIe packaging solutions available on the market today. I will cover solutions from ASE, Intel, Samsung, and TSMC in alphabetic order, as well as some future roadmap directions and new technologies for UCIe.
Are you able to advance, Stefan? There you go.
Yep. So as CMOS technology scaling is slowing down, heterogeneous package level integration is increasing. And we have a chart here on this slide that shows that we have been using monolithic chips for a long time. Unfortunately, they are limited to the reticle size, which is a little bit over 800 millimeters square. If you want to integrate more silicon area in the package, you have to break it down into chiplets. And the other trend that we're seeing is that the memory, the high bandwidth memory, is also integrated into the package, and that enables higher bandwidth and lower power. Then we see 3D stacking, which is enabled by hybrid bonding, and that reduces the interconnect pitch between the die to less than 10 microns. So we have a high density interconnect vertically, and now we can optimize the technology node for each chiplet. So for example, the IO die can stay in a lower cost, more mature process node, because the IO area doesn't scale with the process technology anymore. So it doesn't matter which node you use, while the compute and graphics function can benefit from the more advanced technology node to increase the density and reduce the power. So you can mix and match different nodes on the same package, and that's where UCIe comes in to help interconnect. So now let's start by looking at the ASE packaging roadmap. ASE stands for Advanced Semiconductor Engineering. It's a Taiwan-based company, and they offer a comprehensive package platform. They call this Vertically Integrated Package Solutions, or VI-PAC platform. And that includes the fan-out system in package, or FOSIP, fan-out package on package, or FOPOP, and fan-out chip on substrate, FOCOS, and there is a FOCOS version -B, which stands for bridge, as well as enhanced 3D options and co-packaged photonics. You can tell which company I'm referring to by looking at this little logo on the bottom left corner of each slide. So this slide here shows a cross-section of the ASE 2.5D technology with the TSVs. So you can see the substrate, silicon interposer with integrated deep trench capacitors for decoupling. And then we have multiple chiplets connected on the interposer, as well as possibly some optical chiplets using silicon photonics. So you see a little fiber optics coming out of that. So we'll talk about that more later. And then a heat spreader at the top for cooling. This slide here shows the different flavors of the fan-out chip on substrate, the FOCOS platform. So there are two versions. There is a chip first and the chip last option. So in the chip first, you first lay down the chips, and then you deposit the routing on top of that. The chip last, you first do the interconnect, and then you connect the chips. So it's better because you can test the interconnect before you actually commit the chips to the package. And this technology supports up to 6 metal layers, as well as high bandwidth memory integration. And the fan-out area size can be up to about 50 by 50 millimeters square. This slide shows the fan-out chip on substrate with the embedded silicon bridge. So with the bridge, we have high density die-to-die interconnect, and this also supports a chip first and a chip last option, as I explained in a previous slide. The local silicon bridge enables line and space less than 1 micron, so it's much tighter pitches, much higher density interconnect. And it applies to many different markets that you can see here on the bottom left of the slide. Finally, ASC also enables the complete design flow for chiplet integration, including auto routing and optimization using commercially available EDA tools, as well as the mask generation in industry standard formats. Next, we switch gears to look at Intel's advanced packaging roadmap with 2D multi-chip modules, 2.5D embedded multi-die interconnect or EMIB, and 3D stacked Foveros solutions in mass production today, and hybrid bonding-based Foveros Direct in development. You can see the bump pitch scaling from about 100 microns in the flip chip BGA on the left to less than 10 microns with the hybrid bonding on the right side of the slide. This slide shows the evolution of Intel's package types. We notice the increasing complexity over time with the Ponte Vecchio here in the center, combining both EMIB and Foveros technology, and including 47 tiles spanning 5 different process nodes in an area that is 3 times larger than the typical reticle side. Here we cover the embedded multi-die interconnect evolution, or EMIB, starting with 6 bridges on the left in the FPGA product, going to 10 bridges and 14 bridges in Sapphire Rapids. So there's 10 bridges in the regular 4-chiplet Sapphire Rapids and 14 bridges that enable the integration of HBM memory in the package, and going even higher all the way up to 20 bridges in future products. You also notice the bump pitch here going from 55 micro bump pitch to 45 microns and down to 36 microns in the future with TSV support. This slide shows the Intel Foveros technology roadmap. So we also see a fast pitch reduction from 50 microns to 36, and then down to 25 microns for the conventional Foveros. And Foveros Direct, which uses hybrid bonding, is expected to have a 9 micron microbump pitch and continuing to, in the future, to less than 5 microns hybrid bond pitch. You also notice the increase in the vertical interconnect density over time that will enable very interesting partitioning options in the coming years. Switching gears now to look at Samsung's packaging roadmap, we see a whole spectrum of options, starting with the logic on logic on the lower left and covering multiple memory flavors with different packaging options from 2D to 2.5D and 3D. And you notice the focus on bandwidth, which is a key parameter for machine learning applications. Samsung Logic 3D platform offers both thermal compression bonding, or TCB, using microbumps, which has been in production since 2016, as well as hybrid copper bonding technology, or HCB, to provide higher interconnect density for increased bandwidth. And vertical stacking here enables a significant footprint reduction compared to monolithic design, as you can see on the right side of the slide. For the high bandwidth memory integration, Samsung currently offers solutions for 2, 4, and 8 HBM stacks, with 12 stack options coming next year. All these provide higher capacity and bandwidth compared to the GDDR6 board level integration options, as you see on the bottom of the slide. Samsung also offers embedded Silicon Bridge and RDL-based interposer solutions, with Silicon Bridge having 0.4 micron line and space and RDL using 5 micron line and space. This enables lower cost compared to full-blown silicon interposer solutions. For low power memory integration, Samsung offers fan-out panel level packaging, or FOPLP, and fan-out wafer level packaging, or FOWLP. Both enable small form factors to minimize package thickness, both important elements for mobile applications like cell phones and tablets. Finally, let's look at the TSMC package offerings. There are 3 families. INFO stands for integrated fan-out. CoWoS stands for chip on wafer on substrate. And SOIC stands for system on integrated chips, which is the 3D stacking option with hybrid bonding. So let's look at each of them in more details in the next few slides. The CoWoS platform has 3 flavors. The -S on the left is the traditional silicon interposer option that enables global high-density routing with through-silicon vias and embedded decoupling capacitor option for improved power integrity. The -L is the silicon bridge option that enables local high-density routing. And the -R on the right side is the redistribution layer option with up to 6 layers of RDL at 2 microns line to micron space. The integrated fan-out technology is another platform. It has been in mass production since 2016 and initially was driven by cost-effective mobile applications. The InfoPop was the first 3D fan-out packaging solution to integrate the SoC with memory packages using 5-pitch copper RDL. The Info technology envelope has been extended to apply for HPC technologies, including local silicon interposer info directly on substrate, info multi-chip solutions, and 3D implementations. Finally, the SOIC family is targeting 3D die stacking with 9-micron hybrid bond pitch and is in volume production today. There are two flavors. On the left, there is a chip on wafer, which enables multiple chips to stack on a wafer, and wafer on wafer, which bonds two wafers directly, which is less expensive because it's a single operation, but requires the two chips to be exactly the same die size. If you feel overwhelmed by all the different packaging technologies, you are not alone. To simplify the 3D IC package design, TSMC worked with EDA partners such as ANSYS, Cadence, Siemens, and Synopsys to create 3D blocks, which is an open standard that unifies the design ecosystem with qualified tools and workflows. 3D blocks models the key physical stacking components seen here on the left and the logical connectivity information, and can greatly simplify 3D IC design entry. It can apply to any of the packages that you've seen until now. It's not exclusive to TSMC. Finally, looking forward, advanced packaging technology is also expected to bring optical fiber communications into the package. By moving the optical I/O closer to the SoC, the power overhead from the intermediate SerDes that drives the electrical channel will be reduced. The ultimate goal is to integrate the optical engine into the package, as you see here at the bottom, using 3D stacking technology. And the UCIe Consortium will also look to extend the standard into the optical domain into the future. So in summary, UCIe is an open industry standard that establishes an open chiplet ecosystem and universal interconnect at the package level. The UCIe Consortium is incorporated as a nonprofit corporation since June of last year and has 12 board members. The UCIe 1.0 specification is available on our website. We have over 120 member companies so far. There are 5 technical working groups and 1 marketing group, and they're all meeting actively. You can join as a contributor or adopter by following the simple instructions on our website. And finally, please join us for the upcoming UCIe half-day tutorial at this year's Hot Chip conference, which will be held at the Stanford University. The tutorial will be on Sunday, August 27th in the afternoon. So we're looking forward to see all of you there. So this completes our webinar presentation, and I will now hand this over to Swadesh for the Q&A session. Thank you.
Thanks, Stefan. So been looking at the questions coming in. The first one goes out to Gerald. Is it possible to connect a UCIe-A and UCIe-S chiplet together? Are they compatible?
Thank you, Swadesh. Can you hear me again, by the way?
Yes.
Yes.
Okay, thank you. UCIe-A and UCIe-S chiplets, can you connect them together? No, you cannot. There are multiple fairly important differences between the two different types of UCIe flavors, the advanced and standard. There's significant differences in beachfronts, as we showed earlier. There's signal integrity requirements due to channel differences and physical wire counts, not to just mention that, by 16 versus by 64. So these differences are all intentional for optimization points for the different packaging technologies. Advanced package technologies are allowing you to get the maximum bandwidth densities possible, whereas the standard packages give you that more flexibility or longer channel reach. So trying to make the two compatible with each other, what it would really end up in is degrading the performance of either one, of both of them, basically. So in order to have a separate optimization point for UCIe-S and a separate full optimization for UCIe-A, we're forced to specify them in a way where you can't interoperate them.
Thank you, Gerald. The next one's for Stefan. Can you say a little bit about 3D stacking and what's UCIe's plans related to that?
Sure. Thank you, Swadesh. Right now, we're focused on enabling an ecosystem for 2D and 2.5D package integration, as this is the bulk of the market demand that we're seeing today. We will definitely have a 3D spec in the future. We see that transition coming, and we expect to start working on it not too distant future.
Thank you, Stefan. Gerald, the next one probably you can answer. For UCIe-A, you mentioned a fixed beachfront. At very tight bump pitches, it becomes valuable to shrink both the shoreline as well as the depth. Is this allowed, or will this be allowed in the future?
Thank you, Swadesh. As we discussed earlier, one of the most important values for UCIe is forwards and backwards interoperability. Again, this is to enable people to be able to fully regain or recoup their investment in chiplets. You don't want to have one generation of UCIe in there that is incompatible with the next generation. As an example, I'll give is, just as an example, let's say PCIe. You can take a PCIe 5th generation device and connect it to a 3rd generation device. Of course, the frequency goes, or the data rate goes down, the bandwidth goes down, but you still have that interoperability there. So in this particular case, fixing that beachfront, that 388.8 microns is very important. It's a critical component of practical or realistic mechanical interoperability, as we looked at in that earlier foil. In the future, having said that, in the future, as bump pitches continue reducing, and perhaps there could be maybe future generation versions of the specification that go even below 25 micron bump pitch support, I'm fairly confident that will happen. We can also look into the possibility of stacking the modules similar to that stacked, or by 32 module for standard. And so when we stack that, effectively, you're getting the same equivalent shoreline reduction in terms of bandwidth per millimeter escape. So I think we will probably look at that sometime in the future. But yeah, the shoreline remaining fixed is a critical component for interop.
Thank you, Gerald. Then the next one's for you, Stefan. How do you handle differences in bump requirements for the various advanced package technology offerings at different OSATs?
Okay, so we do expect the underlying UCIe IP designs to be fully portable across all the leading OSATs. So as long as the bumping is done at the OSAT and meets the critical dimensions and the planarization rules, I think this should always be fully portable. And usually this bumping is done at a third party vendor, but overall we do expect compatibility.
And then along the same lines, can you give a little bit more information on where people can get more technical details around the packaging solutions that you talked about today?
Sure. So our goal today is to enable a 2D and 2.5D package integration. And we want to show you what the different package options available are. I'm sure there must be much more. I mean, we only covered 4 major suppliers. But for the technical details, you will have to contact the specific OSAT that you're working with directly. And I also want to mention that UCIe is an open standard. We do not endorse any specific packaging technology or any specific implementation. That's totally up to each customer to pick their preferred implementation.
All right. And then probably the last one for today, we do have a few more that I'll mention. You know, we'll end up publishing a blog response with all of the questions that were in the chat. So in case we didn't get to your question, please look out for that one. Probably a good way to end this, Gerald, would be if you can talk a little bit about compliance and, you know, what are the thoughts in the consortium around doing different testings at different levels of package and wafer testing?
Yes, thank you. Yeah, that is an important one. Thank you, Swadesh. Thanks for the question, folks. So yes, we definitely will be, have been, and will continue working on compliance. This is a very key critical component to any sort of successful I/O standard and adoption. You want to get on that integrators list. You want to get that compliance sticker. So the work group, the technical work group in the consortium that I co-chair, the form factor and compliance work group, is chartered with this very task. Everything related to compliance, this includes anything that is mechanical, anything that is related to electrical, adapter, protocol, the setup, the type of tests that will be run in order to get different levels of compliance. We discuss them in that work group. So anybody and everybody that is interested in that, I encourage you to join the UCIe Consortium and attend the work groups. And that's very much something that is a work in progress, and we are working on a compliance program.
All right, thanks. Back to you, Rachel.
Fantastic. Thank you, everyone. Thank you so much, Gerald, Stefan, and Swadesh, for participating today. As Swadesh mentioned, we will be providing a blog post after the webinar that will include any questions we were unable to address live today. And we will also have the recorded webinar on the UCIe YouTube channel. We'll be following up with you. And if you have any questions, please don't hesitate to reach out to us at press@uciexpress.org. Thank you so much for joining us today. And at this time, we will end the webinar.